So next we will discuss about an important uh, process, random process, which is known as the Markov process. Okay, so I am going to explain about basically about the Markov chains. Okay, so we will discuss about this Markov chains. Okay, Markov chains. Okay, so before going into the Markov chains, first of all I will discuss what is a Markov process. So what is Markov process? So a Markov process is a process in which the future value of the process, or the future value is independent, it is independent of the past values. Okay, it is a process in which the future values are independent of the past value, but past values, but depend only on the present value. Okay, present value. So this kind of process we will call it as the Markov process. Okay, so that means the future value, that means the value at t plus 1, that means the value at t plus 1 time t plus 1, that is the future value, will depend only on the value at t, but not the values at t minus 1 comma t minus 2 etc. Okay, t minus 3 and so on etc. Okay, that means it will not depend upon but not on the values. Okay, sorry, but it will not, but not on the values. That means it will not depend on the values, it will not depend on these values, it will not depend on these values. That means the value at t plus 1 will depend only on the value at t plus 1 will depend only on the value at t. Okay, so this is known as, this kind of process is known as the Markov process. Okay, and it has been named after as the name of the scientist. Actually, the name of the scientist is A. Markov in 1856. It's a very old one, to 1922. Okay, this is his he has died in 1922. Okay, born in 1856. And this kind of process, actually the future values are not depending on the past values. That means the future values are depending only on the present value. Okay, the future value is independent of the past value, but depend only on the present value. This kind of process is known as the Markov process. Okay, next we will discuss what is a Markov chain. What is a Markov chain? That's very important. Markov chain, it is a special kind of Markov process. Okay, it is a special kind of Markov process. Okay, I will use MP for denoting Markov process. Okay, MP, it is showing Markov process. Okay, so it is a special kind of Markov process where the system can occupy only finite or countably finite. Okay, or countably finite number of states. Okay, that means suppose if a system is having lot of states, if the number of states for a system is finite or countably finite, that means the states, as I can define the states as A1, A2, A3 etc., AN and so on. Okay, suppose this is finite, this set, the number of state is finite, or you can count the number of states, that means the countably finite, that means for each state you can assign a real number, you can assign an integer. Okay, so it is the finite number of states. So it is a Markov process with finite number of states. So the Markov process with finite number of states or countably finite number of states or countably finite number of states, that is known as the Markov chain. This is known as the Markov chain. Okay, Markov chain, I will denote it as MC. Okay, so MC is denoting the Markov chain. So Markov chain is a Markov process with finite number of states. So states means it is nothing but the state of the system, you can say. Okay, suppose a system is having a state like x1, x2, x3. Okay, these are all the different state of the system. For example, a state can be some parameters, for example, which is related to the system. For example, it can be a parameter. Suppose if you are considering a system with some numbers, okay, some values, that you can consider these states as some values. We will give an example anyway. Okay, then it will be clear to you, inshallah. So for the Markov chain, actually, suppose if a Markov chain, that means a Markov chain is having a finite number of states. So I can denote the states like this. The states I can denote as a set, which is A0, A1. Okay, I can denote with A0 also. Okay, I have A0, A1, A2, etc. Okay, I have n number of states like this. Okay, these are all the different states of the system. Okay, and these are all some values, can be some numbers. Okay, usually it will be some numbers, some states, like for example, if you are tossing a coin, you have two states, right? That means you can get either head or tail. So head and tail are two different states. Okay, if you are tossing a dice, you have different states. That means you have 1, 2, 3, 4, 5, 6 like this. Okay, these are all the states. But is it a Markov process? If you are tossing a coin, that means the probability, suppose you got it is not a Markov process. Anyway, we will discuss about it later. Okay, so a system, so the Markov chain is having a finite number of states. Okay, so finite, this is finite in the case of Markov chain. Okay, finite number of states. Okay, that is the Markov chain. I hope this part is clear to you, right? So that is for a Markov chain. For a Markov chain, we can define like this: the probability of nth state takes the value an is nothing but, given that x of n minus 1 is an minus 1. So this is denoting the state basically. Okay, and this is the state variable, you can say. This variable is showing the state variable, and this is the state. Okay, so this, the probability that you are going to find out what is the nth state. Okay, suppose the probability that the nth state is an, given that you know what has happened before. That means in the n minus 1th instant you have got the state as an minus 1, and at n minus 2th instant you have got actually the state as an minus 2, and at n minus 3th instant you have got an minus 3 as the state, and so on, and the initial state x0 was a0. So this is some probability. This will be equal to, I told you we are talking about the Markov process, so the future value will be depending only on the present value, or the current value will be depending only on the immediate previous value, not on all the past values. That means it is nothing but the probability that xn takes the value an, given xn minus 1 takes the value an minus 1. Okay, that means we have omitted everything. We have omitted. So what I am saying is that we have omitted all other. That means the past values. Okay, all other past values. All other past values. That means if I am considering the nth instant, it will depend only on n minus 1. If I am considering n plus 1 instant, it will depend only on nth instant. That's it. It will not depend suppose if I am considering like this, if I am considering nth instant, it will not depend on n minus 1, n minus 2, n minus 3. All these are not included. Only actually n minus 1 is included. Okay, so that's what the Markov chain and Markov process. And the Markov chain means the number of states will be finite. It will not be infinite, or it will be countably finite. Okay, so we can define something as the probability that the nth state xn takes the value aj, let's say it is aj, given the n minus 1th state was something like ai. Okay, that means you were in ith state, you were in aith state. Now at n minus 1th instant, the state was ai. Now you are going to the another states, right? That means it is aj, okay, at nth instant. And what is the probability of this transition? That is the probability of transition, and this is known as the transition probability. This is known as the transition probability. Transition probability. Okay, transition probability. So next we will see another important concept, another important definition, which is nothing but the homogeneous Markov chain. Okay, homogeneous Markov chain. What it is? If the one step, this is the one step transition probability, you can say it is one step, because you are changing from ith state to the jth state. Okay, not more than that. So this is the probability of transition from ith state to the jth state, you can say. Okay, in general. So if you have the state I, okay, and you have the state j, so this is the transition probability from ith state to the jth state. Okay, so like this I can represent like this. That means I am moving from I to j. Now if one step transition probability does not, if it does not depends on the time step, then the Markov chain is called the homogeneous Markov chain. Then it is called homogeneous Markov chain. That means here this is known as homogeneous Markov chain. Okay, so this is known as the homogeneous Markov chain. So what is it? That means if the one step transition probability is not depending upon the time that you are observing, that means the transition probability, suppose this, that means the transition from ith step to the jth step, I will represent again. Suppose you have the ith step and you have the jth, this ith state, and this is the jth state, and there is a transition probability. That means there is a probability that you may go to the jth state and now you are in ith state, and that probability is known as probability Pij. Okay, and this is known as the transition probability. I will give you an example, then it will be very clear to you. Transition probability, that means you are currently in a state I, and what is the probability that you may go to is the state j. That is known as the transition probability. Suppose you are observing at n equal to 0, you are observing at n equal to 1, and you are observing at n equal to 2, like this. You are observing at n equal to 100, and so on, or 1000, and so on. Okay, and so on, and you are observing that this is not changing. So this guy, that means this transition probability is not changing. That means if Pij is not changing with respect to time, then you will call the Markov chain as homogeneous Markov chain. So homogeneous means it's same throughout. That means it is stationary. That means Pij is stationary. That means it will not change with respect to time. Okay, so that means the transition probability Pij, that means the transition probability, if you are observing at time instant, that means the transition probability at time instant n and n minus 1, that means you are considering the transition probability from n minus 1 to n, then this will be same as some other m minus 1 and m. That means if you are observing at time t equal to 1 second, Pij, suppose Pij is equal to the probability, it is a probability, suppose Pij is equal to 0.5. If you are observing the same system after 10 second also, the transition probability from I to j will be 0.5. It will not change. Okay, that is known as the homogeneous Markov chain. So we can consider an example now. Okay, we can consider an example. So let us consider the states 0 and 1. Suppose 0 and 1 are the two states of a system. So you have a system with 0 and 1 as the state. So usually it will be represented by using the state diagram. So we are going to represent it by using the state diagram. Okay, this is the state diagram. So you can see you have two states, one is 0 and another one is 1. Okay, so there are two states. Now we can define the transition probability. Suppose you are in state 0 and again you will be in state 0 is nothing but the probability that you are in state 0 and again you will be in state 0. That means this is nothing but P of 0, 0. Now you are in state 0 and you may go to state 1. There is some probability. It is probability 0, 1. Okay. Now you are in state 1 and you may remain in the state 1. That means you can represent like this. That means you are in state 1 and again you will be getting state 1, P11. Now you are in state 1 and you may go to 0 with some probability. You are in state 1, you may go to 0. This is P01. Okay. So if we are considering a particular state, what I am going to say is that suppose you consider this state, you can see here that you have a probability that you may go to P01 with some chance. For example, it's 40%. That means the probability is 0.4. Okay. Then you may sometimes remain in the same state. Then it should be how much? You are in state 0 and there is a chance that you may go to state 1 with a probability 40%. So what is the probability that you may remain in the same state? That is 100 minus 40. That means 60%. Okay, so this will be 60%, or you can say this probability is 0.6. So the total probability, if you consider, so the total probability at the state 0, if you consider, that means P00 plus P01, that means it will be equal to 1, you can say. Okay, next we will see what will be the situation here at 1. Okay, if you see at 1, what is the situation? Now you see you are in state 1 and there is some chance that you may go to state 0 like this. That means there is an 80% chance. Okay, for example, it is an 80% chance that you may go to state 0. Then what is the probability that you may remain in the state 1? Then it is nothing but 20%, right? So if this is 80%, this is nothing but 0.8, and this probability 20% means 0.2. So you can see here P of you are in state 1 and you may go to 0, or means plus you are in state 1 and remain in state 1 is nothing but 0.8 plus 0.2, which is equal to 1. Again you are getting 1. So the sum is equal to 1 here. Okay, so the sum is equal to 1 here, and similarly you can see the sum is equal to 1 here also. That is the beauty of this. Okay, so we can represent this by using a matrix. So we will use the ideas of linear algebra here. So you have state 0 and you have state 1, I told you. So you may go here from 0 to 1, or you may remain from 0 to 0. Okay, so this is nothing but p of 0 1, and this is nothing but you are in 0 and again you are going to 0. Now you are in 1 and you may go to 0 with a probability 1 to 0, and again you are in 1 and remain in 1 with a probability p11. I told you this was 0.4 and this was 0.8. Okay, these probabilities will be depending upon the system. Anyway, this I am giving just an example. Okay, this is not fixed. So 0.2 and this is 0.6. Okay, and so on. So we can represent this by using a matrix. So we can use the matrix representation for this by using a matrix P. Okay, I am going to represent like this. So I in this axis actually I will consider here present state, and here I will consider my future state or next state. Okay, next state. So this is one step transition probabilities. So all these are actually one step transition probabilities, and these transition probabilities will not change. It will not change. One step transition probability and will not change in a homogeneous Markov chain. That's what we are going to consider. So in homogeneous Markov chain, all this will not change. Okay, so you are in state 0, and you may go to state 0 in the next state, right? This is the next state, this is the present state. You are in state 0, or you may go to the next state as 1. Now you can also be in the state 1 and you may go to state 0, and you are in state 1 and you may go to again state 1. So this is how we are going to represent. Now I am going to enter the values here. So you are in state 0, and again you will end up in state 0. It is nothing but the probability p00, right? You are in state 0 and you end up in state 1. It is nothing but p of 01, right? Now you are in state 1 and you end up in state 0, that means p of 1 to 0. You are in state 1 and you end up in state 1 is nothing but p of 1 1. So in our case, actually our matrix will be looking like p equal to 0. Okay, I will use p00. So in our example, so this example is giving you p, that means you are in state 0, you may go to state 0 or 1. This is the present state, and this is the next state. So next state means it's also 0 and 1. Okay, so we are here, you can see we have only 2 states. So it is a finite, it is a Markov chain. That means it is a finite number of states. It's a Markov process and it is a Markov chain also, because it has only finite number of states, and also this transition probability does not change, are not changing. So it is a homogeneous Markov chain. Now you can see here that 0 to 0 we have the probability 0.6, and 0 to 1 we have the probability 0.4. Okay, and 1 to 0 we have the probability 0.8, and 1 to 1 we have the probability 0.2. Now if you see, if you add the elements of this row, you can see here that 0.6 plus 0.4, again it is equal to 1. And if you add here also 0.8 plus 0.2, again it is equal to 1. So this is the property of the state transition matrix. So we will this is a transition probability matrix. So we will call this is a matrix with probabilities. Call the P as the stochastic matrix, because it is a matrix with probability, stochastic matrix. Okay, stochastic matrix. And also we will call, also P is also called the transition, because it is talking about this, it is completely defining the transition probabilities. So transition probability matrix, okay, it is nothing but the transition probability matrix, or usually we will call TPM, transition probability matrix. Okay, so we can see one example of a random walk. Okay, I will see something like a random walk. So an example of a random walk. What is a random walk? A random walk actually defined as a person is walking. Okay, he is having streets. For example, he is having 3 states. He can remain in 0 or 1 or 2 or 3. Okay, and he is walking from 0, for example. Then he can move here, or he can move back. If he is in 1, he can move to 1 to 2, or 2 to 1, or 1 to 3 to 2 to 3, and 3 to 1, etc. like this. Okay, so a person, but this random walk actually it is defined, a person will not remain in same position. Okay, he is having 4 positions, 0, 1, 2 and 3. That means 4 states are there. There are 4 states here in this problem. There are 4 states. You can have more states also. Okay, there are 4 states. That means 0, 1, 2 and 3. Okay, these are all the states. And so it is a homogeneous Markov chain anyway. So a person will not remain in the same position. Okay, will not remain in the same position. That means if this guy is, that is we can define like this. So a person will not remain in the same position. That means if he is in 0, he will not remain in the 0. That means what is the probability that he remains in the 0 and in the next state also? Suppose he is in 0 in the current state. In the current state he is in 0. In the next state also he is in 0, means he will not remain in the same position. That means that probability will be equal to 0. Similarly, if he is in 1, in the next state also will be 1, that is equal to 0. So this is a special kind of process I am defining like this. And if he is in 2, the probability that again he is in the state 2 is equal to 0. That means if he is in 2, he may sometimes walk to 1 or sometimes walk to 3 with some probability. Okay, and if P33, similarly it is equal to 0. Okay, so this is a random walk I am going to define. Okay, now I am going to assign some probabilities for this example. Okay, so I have basically I have some 4 states. I have 1, 2, 3 and 4. Okay, now you can see here I am going to define here, this state can be 0, this is 1 and this is 2 and this is 3. Okay, and this 0, 1, 2 and 3, this is the random walk, the person is walking. Okay, now you see here he can walk from 0 to 1 and 1 to 0 also. But if he is in so he can walk from 0 to 1. I am going to express like this. So it is the probability from 0 to 1. And he will not, the probability that he remains in the same state. That means P of 0, 0, it is equal to 0. It has been given. P of 0, 0 is equal to 0. Okay. That means he will not remain in the same state. Okay. That is this kind of random walk. Now he can from 0 actually whether he can, we will see what is the probability that he moves to 3. We will see here the probability of 0 to 3, we will see now. And he can move from 0 to 2, whether it is there we don't know. Anyway, inshallah we will see here. Okay, 0 to 2. But you can see here in this random walk, suppose this guy is in 0, he can move only to 1, he cannot move to 0 because he need 2 steps for that. In the 1 step actually he can move to 1. So he can move to 1 with some probability, but he cannot move to 0. He cannot move to 0 also. He cannot move to 2 because he need 2 time steps. So this probability is equal to 0, right? And he cannot move to 3 also, okay, because he is in 0. So that probability is also equal to 0. So what will be this probability? This probability will be equal to 1. So definitely if he is in 0, he will be definitely moving to 1. Am I correct? Yes. Now this is the probability matrix. I am going to write it here. P, okay, you can see here he was in 0, 1, 2 and 3. Okay, he may go to 0, 1, 2 and 3. Okay, sorry, 0, 1, 2 and 3. Okay, so from 0 to 0 the probability is 0, and 0 to 1 I told you the probability is 1. So this is next state and this is the present state. Okay, and from 0 he cannot move to 0, so the probability is equal to 0, and this probability is also equal to 0, and if you sum it you can see the sum is equal to 1. Anyway, the sum is equal to 1. Now we will see the another part. We will see another part. Okay, I will use a different color, that's better. Okay, now you are in state 2. From state 2, what is the probability that again you are in state 2? I told you you cannot remain in the same state, as by definition given for this example. The person will not remain in the same state, that's why. So that will be equal to 0, right? So that probability is equal to 0. So P of he is in 2 and he is in state 2 and again remains in the state 2 is nothing but it is equal to 0. Okay, I will not consider this, that's better. I will consider in sequence, because we have considered 0, now we will consider 1. Okay, if he is in 1, again he remains in the same state 1. What is the probability of 1, 1? That is equal to 0. That means if he is in state 1, again he is in state 1, that will be equal to 0. And from 1, actually suppose he is here, he can move back or he can move front, right? He can move left or right. That means he can go to 0. He can go to 0 with some probability, the P of 1, 0, and he can move to 2 with some probability, right? P of 1, 2. There are 2 possibilities. But he cannot move to 3. If he is moving to 3, that means P of 1, 3, definitely it will be equal to 0, because there is no possibility. So P of 1, 3 it will be equal to 0. Now we have 2 things. Okay, I am assigning some probabilities. That means P of 1 to 0, I am assigning P of 1 to 0, I am assigning something like 0.3. Then P of 1 to 2 will be definitely 0.7. P of it will be 0.7. Okay, because the total probability should be 1. So it is 0.3 and 0.7. Okay, I hope this part is clear to you. Next is basically we have next is second state 2. So from the state 2 I can move to, okay, from state 2 I can remain in the same state. Is it possible? No. P of 2, 2 I told you it will be equal to 0. So 2, 2 means this is 2 and this is 2. So this will be equal to 0. Okay. So from 2 I can move to either 1 or I can move to 3. So I can move to 1 with some probability, sorry, not this one. I can move to 1 with some probability. So P of 2, 1, and I can move to 3 with some probability, P of 2, 3. Okay, and I told you he cannot move to, from 2 he cannot move to 0. So 2 to 0 there is, it is nothing, it is not possible. So P of 2 to 0, that is equal to 0. So 2 to 0 is 0. Now I am going to assign some probabilities for 2 to 1. So for 2 to 1 I am giving something like 0.3, some probability. Okay, 0.3. There are some ways to give this probability. According to the problem it will change. Okay, this I am giving an example anyway. So 2 to 3, and P of 2 to 3 is again it will be 0.7. So this should be 0.7 because total sum will be equal to 1 anyway. So if you sum here everywhere, it will be 1. Now you are in state 3. I will use another color, black one. Okay, you are in state 3. What is the probability that you again remain in the state 3? P of 3 comma 3, that will be equal to 0. I told you it will be equal to 0. And from 3 you can move to 2 only. There is no other possibility. Since you cannot remain in same state, the probability you can move only to 3, 3 from 2. So 3 to 2 you can move with a probability 1, because there is no other probability, there is no other way to move. That means from 3 you cannot move to 1. So you can move to from 3 to 2 with a probability of 3 2, which is equal to 1. And from 3, if we are moving to 1, there is no chance, so P31 is equal to 0. Similarly, from 3 to 0, P30 is equal to 0. And from, okay, so all this will be equal to 0. So you got a state transition matrix. So this is how you can basically consider the state transition. Okay. Now I think this is clear to you. Okay. So the Markov process, there are a lot of examples for the Markov process. Okay. Suppose you are playing a chess, you know, chess game. Okay. So you have a lot of things like queen, king, queen, okay, horses, all these things are there in the chess, okay, in the chess game. Okay, so the next movement in the chess game, the next movement will be depending upon the current state. What is the situation in your current state? It will depend upon the current state. Okay, you will not be going through all the previous movement. It is not relevant now, because what is the present situation? According to that, you have to make a decision and move the okay, you have to make a movement. So it will be depending only on the current state. So the next movement depend upon only on the current state, but not on all previous states. So this, you can say, this chess game, you can say this is a Markov process anyway. Okay, and next one, I will give you another kind of Markov process. Suppose there is a sum process. So this is example 1. So next I will give examples. So next I will give another process, which is sum process. So example 2, which is a sum process, which is defined like this: the sum of the numbers at nth instant is nothing but x1 plus x2 plus etc. up to n numbers. Okay, that means this. So this is the sum process. That means Sn minus 1 will be nothing but x1 plus x2 plus up to xn minus 1. So you can represent xn as sum at n minus 1 plus xn. So you can see here that this process, the probability that your sum takes some value, the probability that your sum at Sn minus 1 takes some value an plus 1 is given that you know what is Sn. Okay, similarly, or you can say Sn plus 1 is nothing but Sn plus xn plus 1. Okay, both ways are correct anyway. So the the probability that Sn plus 1 will take the value an plus 1 is nothing but it takes the value an plus 1 is nothing but, if you know Sn was an, Sn minus 1 was an minus 1, etc. up to S1 was a1, this probability will be same as the probability that xn plus 1, sorry, is the probability that the current state, it is nothing but the probability that Sn1 plus take the value an plus 1, sorry, takes the value an plus 1, takes the value an plus 1, given that your Sn was an. That means if you just know the Sn, because it is depending only on the Sn, so that means, so Sn plus 1 is depending only on Sn, so we can say that it is not depending on all the previous things. It is not required at all. You just need to know what is the state you just need to know what is the state at xn plus 1. That means you have to just you just need to know the state, what is the probability that xn plus 1, because your sum will be depending upon your sum will be depending only on xn plus 1. It is nothing but the probability of xn plus 1, which takes the value an plus 1 minus an. Okay, sorry, it is nothing but this is nothing but the probability that your xn plus 1 takes the value an plus 1 minus an. So if you know if xn plus 1 is taking the value, this is nothing but the probability that xn plus 1 taking the value an plus 1 minus an. Okay, so you can say that this is a Markov process by this, okay, by all this condition, because it is depending on only on the immediate previous. Okay, and the next process you can say is a Poisson process. Example 3, a Poisson process. Okay, and Poisson process is known as the counting process. Counting process. That means you are counting. So counting means you will be dealing only with the integers. Okay, how many numbers, that is the counting process. Okay, so the number of counts at the time tk plus 1 will depend only on, it will depend upon the previous count ntk plus the number of arrivals, at k plus 1. That means you can consider like a queue. You have a queue, big queue, the people are standing here. Okay, there is an office. Okay, people are standing here like this. Okay, and you have the time tk. At time tk you have number of peoples and tk, and at time tk plus 1, suppose 2 peoples are coming, then you will be getting ntk plus 2. If 3 peoples are coming, you will be getting ntk plus 3, like this. Okay, number of peoples as total. So the number of peoples which are coming at tk plus 1 as let's say, suppose this ntk is equal to j, and at tk plus 1, suppose at tk plus 1, we can say at tk plus 1, you have ntk plus 1, which is equal to suppose this ntk is equal to I, okay, and at ntk plus 1 you have j number of peoples. Then you can say that how many arrivals are there? Number of arrivals are j minus I, right? So j minus I arrivals are there. So we will deal about the Poisson process in detail, okay, after finishing the Markov process. So what I am going to say is that number of arrival is I. So the probability that number of peoples at tk plus 1, given that number of what I am going to say is that the number of the probability that number of peoples at tk plus 1 is equal to j, given that you know the number of peoples at tk was I, okay, and also you know many things like number of peoples at tk minus 1 was something like xk minus 1 and so on, you know, up to t1 there is no use anyway. Up to t1 it was x1, then this probability will be nothing but you just need to know only the number of peoples at time tk. This is nothing but probability that n tk plus 1 is equal to j, given that n tk is equal to I. Okay, so it is not depending upon all these previous, these things, these informations are useless now. Okay, and only this information, this part is useful, this part is useful, and you can see this is repeated here. Okay, so only this is useful here. That's why it is a Markov process. Okay, it's a Markov process. And another important process another important Markov process is the Wiener process. So Wiener process, it is named after the scientist Wiener process. Okay, and the Wiener process, actually it is a Gaussian process anyway. So Wiener process is having a probability density distribution function, probability density function, x of t k plus 1, x of t f of x of t k plus 1, x of k plus 1, given x of t k takes the value xk comma x of tk minus 1 takes the value xk minus 1, and so on up to x of t1 takes the value x1. Even though if you know all the information, this density function will depend only on this information. So this will be depending only on fx of tk plus 1, which takes the value xk plus 1 given x of tk, which is equal to xk. Okay, this probability, and you can see that all other information, these are all not used. Okay, because it will not depend upon all these factors, and this density function is given as 1 by root 2 pi into alpha into tk minus tk plus 1 minus tk, okay, into exponential of, you have to consider this exponential factor, half of x of k plus 1 minus xk the whole square. Don't need to remember this thing. Okay, I am just giving an example to introduce you what is Wiener process, and this alpha into tk minus 1 minus tk. Okay, that's it. So this is the Wiener process, and the Wiener process is Gaussian in nature, is Gaussian, and it is also, it is a Markov process, and it is a Markov process, and a Markov process. Okay, it's a Markov process. So this is not a Markov chain, this is a continuous time process anyway. Okay, we can say this is a Markov process. Anyway, with the integer valued Markov random process, we will call it as Markov chain, and the Markov chain is having some properties that we have seen. Okay, and the homogeneous Markov chain also we have seen. I hope this part is clear to you. Next, we will consider an example that's a very important example. Consider an example. Suppose there are three supermarkets. That is, there are three supermarkets. Okay, you can consider Otaim, Panda, and Al Raya like this. Okay, so there are three supermarkets. One is A, and another one is B, another one is C. So there are three supermarkets, and this A has for example 200 customers. Okay, okay, and this B has 120 customers, okay, and C has 180 customers. So we can say this is the initial customers, okay, initial values at time 0, okay. So at time 0, suppose you have a supermarket, you are observing how many number of customers are there in the supermarket at this particular, on this particular day. You are starting from now onwards, and you are going to count, and you are trying to judge something, some parameters on some comments on it, okay. Anyway, what I'm going to say is that on the present day, now we have 200 customers currently on for A, and 120 customers for B, and 180 customers for C, okay. So we can see this as the initial probabilities. So how to define the initial probabilities for this? So we are going to define the initial probability distribution for this, probability distribution, or mass function you can say, because we are talking about discrete string. Probability mass function, we can say it is P0, okay. You can use different types of notations are there, P0, and it is a vector anyway, okay. So how to define this? So we can define A0, B0 and C0 has different probabilities. We have 200 customers for A, and out of that we will divide it by total number, so 200 plus 120 plus 180, okay. So you will get it as 0.4. That means 40% of the customers are there for A0, okay. So this is nothing but P of 0, P1 of 0. Similarly for B, you have 120 divided by the total, same thing, this is the total, okay. So you will get it as 0.24. So 24% of the customers are therefore are belonging to B0, okay, sorry, for B, okay. P, this is P2 of 0, okay. And the third one, you have 180 customers divided by the total, so you will get it as 0.36, and it is P3, right, okay, like this. So these are all the initial probabilities we can define for a practical problem like this. You can see that in Jarir and all, when you enter the supermarket, you can see there is a counter, they have placed a counter. So based on this counter, actually they can calculate lot of parameters. So this reading will be taken and it will be modeled as Markov process using some softwares are available for this. So by using some softwares, this information will be directly fed, and by using the theory of Markov process, they can actually compute the situation, okay. So that's what we are going to see, what will happen, whether the number of customers will be increased or decreased, or what is the situation of their business. Everything can be calculated by using this, okay. So we are going to define the transition, okay. We are going to define the transition, okay. Now the transition probability. So in the previous example, let us assume that you have okay, you have A with 200 customers and you have B with 120 customers, okay, and you have C with 180 customers. This is the initial value, okay. Now suppose if there is a customer which is going to the supermarket A, he will again remain in the same, he will come to the supermarket again the next time is 80%, for example, okay. And if he may go to the other supermarket, that means A to B with some probability, that means 10% of the customers which is already from A is going to supermarket B, okay, at the next time, and some customers from A will also go to C next time. So this you can see, this is 80% and this is 10%, so the remaining also will be 10%. So when you consider the things which are leaving from A, you can see that 80% of the customers will be coming to A again, 10% will go to B, 10% will be going to C. Okay. So next we will see what is the situation regarding B. And from B, some customers will remain in the B itself. That means 70% of the customers will come into B again. Okay. And from B, some customers will go to A, and it is suppose some 20%. Okay. And this information has to be collected by knowing all the supermarkets and all the lot of things, informations are needed to model this thing. Anyway, I am giving just an example. And from B, some customers may go to C, and you know that this is 70 and this is 20 customers, and then it will be should be 10. Okay. Next is there are some customers in C which may go to C again with some probability. This is 60%. And from C, some may go to A, some may go to A with a probability, let's say this is 10%. And the 30% of the customers will go to B. Okay, like this. So in this situation, you can express the transition matrix P as A, B and C. Okay, like this. This is the present state, and the next state is also A, B and C, like this. So A to A, I told you 80%. So A to A is 80%. You can say it is 0.8. And from A to B it is 10, that is 0.1. A to C is also 10%, 0.1. And from B to B, you know that it is 70%, and B to A it is 10%, that is 0.1. Some B to C we have seen it is 0.1, and C to C we have seen 60%, that means 0.6, and C to A it is 10%, and C to B is 30%. Okay. Now you can see if you sum all these things, it will be 1. The sum will be 1, right? The sum will be 1 here. That is the property of the stochastic matrix. So the stochastic matrix is having the probability. Now you know that the initially we have seen how many customers are there for this. Okay, how many customers are there for this? Okay, for A naught initially. So this is at the initial time. So we have our probability at initial time as 0.4, this is for A, and 0.24, we have seen this already. Okay, 0.24 for B, and 0.36 for C. So this is our initial probability. Now we are going to calculate something. Okay, how many customers, suppose I am going to suppose we are calculating at time n equal to, we have already information at n equal to 0, so we are calculating at time n equal to 1. Okay, next day for example. So you can see this is at n equal to 0, you have initial contribution. What is now, how many customers will be there in A? That is what we are going to calculate. Okay, I hope this is clear to you. The problem is very clear to you. So we are going to calculate how many customers will be there in A. So you see here I am considering A, and I had how many customer? Okay, I will just consider the node A. I had 200 customers, and 200 customers, out of that 80% will again come into A, and 20%, right? 10% will be going to B. 20%, sorry, 20% is going to B, and remaining some 10% will be going into 10%, sorry, 80 and 20. Okay, this is not 20, this is 10, sorry. 10% will be going into B, and 10% will be going into C. Okay, C. So, and what are all the new things which is coming into A? That's what we have to account. From B, something is coming to A and it is 20%. Okay, 20%, sorry, 20%. And from C, something is coming into A. How much? 10%, right? 10%. 10% is coming into A, right? I hope it is clear to you. So, whatever which is whatever there are, how many customers are coming again into A, it is 80%. So, what will be the number of customers in A at n equal to 1? That's what we are going to calculate. So, there are 200 customers in A. Out of that, 80% is going again into A. Okay, 80% means 80 by 100 plus. And how many customers are in C? In C, 180 customers are there. And in B, we have 120 customers. So, 180, so we are talking about B now. So, this is the situation from A to A. And now we are some customers from B also will be coming to A. How much it will be? It is nothing but 20%. Okay, so 20%, that means 20 by 100. How many customers of B? That means 120 customers are there. Out of that, 20% is coming again into A. Plus, we have how many customers in C? So there are some customers which is coming from C to A also, right? So 180 customers are there in C. Out of that, 10% is coming to A. Okay, so what will be the total number of customers? So if you add all these things, you will get the total number of customers total at A. Okay, total, this will be the total number of customers at A at time instant 1. So at n equal to 1, this will be the total number, total at A. Okay, at time instant n equal to 1. Similarly, you will get for B, you will get for A, so we will get for C also. Okay, all these things can be calculated. So after calculation, you will see how many number of customers are there in A, B and C. Similarly, you can calculate for n equal to 2, n equal to 3. So after a week, after 7 days, that means n is equal to 6, because we have started from n equal to 0. So n equal to 6, at n equal to 6, you can see here that how many customers will be there in A and how many customers will be there in B. Okay, so this is the use of the state transition matrix. So this probability can be easily calculated by this way. Okay, so I hope this part is very clear to you. Okay, so this, that is, this can be easily calculated. You can easily calculate this phenomenon. You can easily calculate by using the stochastic probability matrix and the initial probability, stochastic probability matrix is P, and the initial probability mass function, that is nothing but P0. Okay, so if you know these two factors, you can easily calculate. Okay, this you see I have just written only for A. Similarly for B you can calculate, similarly for C you can calculate. So how you can calculate this? If you know the stochastic probability matrix or the transition probability matrix, okay, transition probability matrix, okay, you can see it is transition probability matrix. Okay, you can also name it as transition probability matrix. So if you know transition probability matrix that we have defined here for this problem, this is the P, that's what we have defined here. And if you know this guy, that means the initial probability distribution, you can easily calculate by using P0. This is a vector. You multiply this, then you will get P of 1. Now this is the case for n equal to 1. Now for n equal to 2, you can calculate you have P1, again you will multiply with P, then you will get P2. Okay. Similarly, for P3, similarly, if you know P2 and if you multiply with P, you can calculate P3. So this kind of thing, it will, so after getting, so this will be giving you a probability. If you know the probability and if you know the total number of customers, suppose if it is fixed, then you can see here that for at any time instant n, you can calculate what is how many customers will be there in A, how many customers will be there in B, and how many customers will be there in C. Okay. And this kind of phenomenon, if you proceed like this, P3, if you know P3, you can calculate P4 as P3 into P. Okay. So like this, and so on and so on. So for our example, we have our P, which is equal to 0.8, 0.1, 0.1 and 0.2. I am just rewriting the previous matrix. Okay, this matrix. Okay, I am rewriting it again. So P 0.2, 0.7 and 0.1, and this is 0.1, 0.3 and 0.6. Okay, and initial distribution P0 was given. We have already calculated it. Okay, what was it? We have seen already. Yeah, we have calculated by using this idea. Okay, this is how we can calculate 0.4, 0.24 and 0.36. Okay, 0.4, 0.24. Okay, we will use as a matrix representation 0.4, 0.24 and 0.36. Okay, now how to calculate P1? I told you P0 multiplied with P, which is equal to 0.4, 0.24, 0.34, simple matrix multiplication, then 0.8, 0.1, 0.1, 0.2, 0.7 and 0.1, 0.1, 0.3 and 0.6. So this is how you can simply calculate this. Okay, so after getting, then you will be getting some value. Okay, for P1. Okay, I am not going to calculate this, and after getting P1 you substitute here, and again you have the matrix, multiply this with this, then you will get P2 at time instant 2, or the second day or third day, you can say. So this is what. But if you proceed like this, you can see that P of 7, for example, P of 7 will be equal to P of 6 multiplied with P, right? And P of 8 will be equal to P of 6, P of 7 multiplied with P, right? So you can see here in general, you can sometimes you can see here that sometimes you can observe that P of 7 will be equal to P of 8. If you calculate again, it will be going almost the same, that P of 9 will be equal to P of 10. It is converging, you can say it is converging. So that means it is converging to some value. Converging, that means it has been gone to a convergence. So this will happen only if the matrix P is a regular matrix. Okay, matrix P is a regular matrix. And what is a regular matrix? That's what we are going to see. So this kind of convergence, so convergence will happen if P is regular. Okay, the P is regular, and you can see here that if P is regular means P is regular means the nth power, that means the P raised to n has only non-zero positive entries. Okay, if P has negative entries, then it will not work. Okay, for example, you have P is, suppose it is 0.25 and 0.75. You can see it is 1. It is a stochastic matrix. 0.5 and 0.5, again it is 1. Then if you calculate P square, you can see it is 0.438. P square is nothing but P multiplied with P. So 0.438 and 0.562, 0.375, 0.625. Okay, and you can see this is a regular matrix. Okay, this is a regular matrix. And similarly, for example, another example, if P is equal to 1, 0, 0.5 and 0.5, so P square will be equal to 1, 0, 0.5 and 0.5 multiplied with 1, 0, 0.5 and 0.5, and this you will get it as 1, 0, 0.75 and 0.25. So again you can see that this is also positive entries. So this P is a regular matrix. Okay, regular matrix. If P is regular, then the Markov chain is called homogeneous. Our homogeneous Markov chain will be is regular. If P is regular, then we will say the homogeneous Markov chain is also regular. So it is known as the regular Markov chain, homogeneous Markov chain. Okay. So in the previous example, I have already okay, this is the we will see. Suppose I told you in the previous example, sometimes you can see it is converging. Okay, you can see it is converging. Okay, I will just explain with the values for the previous example. So in the previous example, we have P is equal to 0.8, 0.1 and 0.1 and 0.2, 0.7 and 0.1 and 0.1, 0.3 and 0.6. Okay, 0.6. Now P of 1, I told you it is P0, that means 0.4, 0.25 and 0.36. Okay, am I correct? I need to check it. .24, right? It is 0.25. No, it's not 0.25. 0.24. So into P, you will get the answer as 0.404, 0.316 and 0.280. Okay, that's it. Now you can calculate P2 as P1 into P, and this is nothing but your P1. So you can calculate P2 and so on. If you do this, you can see the values will be something like P7 is 0.455, 0.354 and 0.202. Okay, and P8 is 0.455. Again you will get it 0.35, 0.202. That means this is almost equal. That means it is converging. So this will happen only if your P is regular. That means this P is a regular matrix. That's what I have explained before. So after convergence, you can see here that this is 0.455. Then how many customers will be there for A? So we have A has how many customers? At the end, after convergence, 0.455 multiplied with the total number. Total number was 200 plus 120 plus 180. That's what we have seen. So this much number of customers will be there for A. Okay. Next, for B has, actually you can see the value is 0.35. So B has 0.35 multiplied with 200 plus 120 plus 180. This much number of customers. This is the number of customers, okay, for A, B and C. Okay, similarly for C, you have C has this much number of customers. C has 0.202 multiplied with the same number, okay, same number, this much number of customers. So at the end of some 1 week, you can say, or it's after 8 days or 10 days, you can see that this is converging. That means C has some customers, very less number of customers, and A has more number of customers, and B has something is between. So this guy A is having more customers, and this C is having less customers. So C has to make something to attract the customers, right? That means he has to change his transition probabilities. He has to change the transition probabilities. So he has to make a new policy such that he has to give some new offers or something like that, okay? Then only he can escape from this, okay? That means he has to completely change the transition probability. If he is continuing with the same policy, he will be in loss, okay? Because only 20% of the customers are coming to C at the end of the day. That means if Pn, you can see here P7 is equal to P8. Let's say all this, again you will be getting P9. If he is continuing like this, I can say that this is equal to some value pi. That means when it reaches, this is after convergence, okay, after convergence it will be converging into some number. You can see this pi for our example, this is our pi, this is also same. That means it is converged. So after convergence, the probabilities we will call, this is the probabilities after convergence. So after convergence we will call these probabilities as pi. So P10 will be equal to P9 into P, but I told you P9 was pi, and after convergence P10 also will be equal to P9, and you will be getting this also will be equal to P10. It will be equal to P10. All will be same. It is converged. That means you can write like this. The equation you can write like this: pi will be equal to pi into P. Okay. So, or in another way, pi into P will be equal to pi. So this will be the situation at convergence, after convergence. Okay. I hope this is clear to you. So regarding this this matrix notation, basically regarding this concept, we can prove it mathematically, and this is nothing but whatever I have told you now. It is known as the Chapman-Kolmogorov theorem. Okay, this is actually I have written in a very simple way anyway. This is known as Chapman-Kolmogorov theorem. Okay, so we will prove this theorem in the next class mathematically. Okay, this is just we have explained with our logic. Okay, this is nothing but the Chapman-Kolmogorov theorem. So I hope this part is very clear to you. Okay, thank you.